Okay, welcome everybody for another Friday seminar at JKMRC. We have another external presenter this morning. His name is Helgi Stedman. He is a principal geologist at THIESS, and he studied metasomatism processes in New Zealand at the University of Victoria. He came in Australia in 1998 and started working in the coal industry. From 1998, he was involved in exploration, engineering, and modeling. His topic is adding blast holes to exploration for improved coal recovery and modeling. Helgi, the floor is yours. Welcome.
Thank you everyone for coming along. I hope to impart some enthusiasm for this topic that I have at THIESS. On a daily basis I get to work with this material, and it really does mean that I don't have much work to do because I love this topic so much. So, adding boreholes, blast holes to exploration, we have an exploration suite, which is typically 200 metres apart, boreholes 200 metres apart for exploration, and then we have blast holes which are typically 20 metres apart. So we have a very fine, detailed amount of data, and putting that into a very coarse arrangement of holes. And this presentation will show you the things that we can see. So exploration establishes what we have, and so we can start to do feasibility work. It means drilling, of course. Once we're mining, blasting is essential. Also means drilling. If one does not blast from an exploration hole, but with geophysics one may explore from a blast hole. Of course that's not in reverse, you can't blast an exploration hole. But this presentation shows what is uncovered by logging blast holes in a coal environment. So I'll just take you through a few areas where THIESS works in the Bowen Basin. We have mines around Blackwater, recently inherited a mine called Jalmbar Plains, and there's also Curragh. There's Lake Vermont, there's Burton, and up here I've got an example from Collinsville. But recently we've inherited the Sonoma project. So I'll just have a look at a few dry facts first. What is a blast hole? A blast hole is a 29 centimetre diameter hole where we charge with ANFO. I instruct a certain number of holes to go through the base of the coal, and that's so that the geophysics, when run, can see the floor of the coal, and so we have a roof and a floor that is easily seen in the geophysics. Typically though, the blast holes will stop above the coal. So why log blast holes? And that's to create an accurate roof model, and with an accurate roof model we can then start to protect the coal roof. And that's all about placing the charge in the right place, because if we don't place it in the right place, it's gone to smithereens. Only then can you consider dig design, equipment selection, machine guidance, and stripping method. It all starts with putting the charge in the right place. Once that's there, then you can start to look further on forward at these items. So let's have a look at a few, the setup of the benches at Lake Vermont. And these thick lines represent the holes. So angled here for the angle of the high wall, but in the middle here we have a vertical. So I collect data from each of these holes, separated by 60 metres. And so we're stripping to the Leichhardt seam and to the Vermont seam. This is a mid-strip set of holes, pre-split line flanks the block which is in question. So here's a look at the drill rig drilling the vertical holes. This is the floor of the Leichhardt. And once the model is made, once the roof is created, then the drill rigs can start to produce the holes for the overall cast shot. When I say cast shot, when I talked about stripping method before, the method can either be cast or we can dig it off with a shovel. But this is particularly it's to cast this rock away.
Excuse me, just to figure out, there's a cord that you're keeping on the floor there, which you're going to take down, so it's warning you about tripping against it.
So that'll be extra. Okay, we're going to have a look at some geophysical traces from the blast holes. Probably got to hit the lights on this one.
It's the top rock.
Top one?
No.
Alright, this is looking at a typical trace from one of the blast holes. Well, we can just looking at the orange is the natural gamma, and the blue is the induced gamma that we get from the tool. These are two separate runs. This is what's called a dummy run. There's no source, radioactive source on this one. This trace is picking up the background radiation of rocks. This signature here is mudstone. The reason it's mudstone is because mudstone is mildly radioactive, having potassium-40, uranium, thorium, just as bananas and Brazil nuts are radioactive. Mudstone is because it's got potassium-40 in it. Coal is not radioactive because it has less clay or less potassium. And the trace that I use to pick the actual roof is the density trace, which is the BRD with bed resolution density. And that gives me the detail for the fine point that I need, which is the inflection point between background host of the background waste rock and the maximum density, low density. So it's basically in there, the inflection point. This anomaly here, unfortunately the white lines have cancelled out of it, but that's what's called the Yarrabee tooth, and that's a highly radioactive compared to the other rocks in the background. This is a nice marker band that I can use when I have more repeating sequences. I can trace exactly where I am, and also it lets me know that yes, in fact, this is the Vermont seam because the Yarrabee tooth sits underneath the Vermont seam. So looking at the high wall that that blast hole would have come from, we've got the silty sandstone, there's that mudstone, there's 6 metres of Vermont. So I'm going to overprint that trace on this wall. And the reason why the top doesn't match that top is because this hole was further up dip. But I can line up the mudstone and the coal. So you can see the gamma reacting to that mudstone. And it's important to know the mudstone because the drill and blast engineer is interested to know the competency of this rock. If I can give warning to the drill and blast engineer that in fact this rock is almost free diggable once you've shattered the top here, then the charge can be actually loaded a bit higher. And conversely, if that's a hard sandstone, then the charge can be brought a bit further down. So this is what will occur if, this is a demonstration of what will occur if we don't know the right place to put the charge. This is taken from Collinsville, and that was, the blue line was the roof of coal. And I just want you to have a look at this. In this section of the cast is different from this section of the cast. This has been loaded with respect to the roof, and in this section there is very little respect to the roof. The charge is a lot lower, and so you'll notice here that the coal comes out like a set of drawers, whereas the coal here stays in situ as this starts to cast away, because the charge, whoop, let it run. It's the old-fashioned method. The charge is being placed at a point above the coal where there is no movement here, very little movement. When we get to here, you'll see this piece of coal get lost. It's starting to move away. This is a great demonstration of putting the charge in the right place with respect to the roof of coal. So now I want to have a look at thickness variation, sort of things that we can pick up in, for our model. I'm going to move away from putting the charge in the right place now and just look at the thickness variation here is very, very regular and boring, predictable for a geologist. So far, it's very, put that in there for the yawn. Still interesting though. Sometimes it gets weird. And yes, I can start to squint at that and wonder what the hell is going on in that situation. In fact, this is a thrust fault plane running at an angle more like this. It's not, if you're looking at the high wall, this is an oblique photo, but that face of rock there is the angle of the thrust coming in at that type of angle. Here you can see pre-split holes, barrels, that have come through to assist with the removal, the exposure of that batter. So the question is, how do I protect, or how do we protect the coal that is in that situation? When I'm presented with, I have to turn this off again.
Second bottom, yep. One more.
Okay. This is a situation where we have a blast hole with regular geology. Here's a Yarrabee tuff. This is a Vermont seam. Another hole has actually intersected nearly twice, or over twice as much Vermont as there is in this hole. And in here it's repeated, like so. The point here is to always protect the roof, so this is going to be one point in the model. Here's the other point, and here's the other point. And looking at the high wall, this is looking straight onto the high wall with our pre-split sweep. The blue is the coal, and so you can see that the thrust plane and the Yarrabee tuff in here repeat Yarrabee tuff here. You start to see the plane thrust over the footwall of this Vermont seam here. See a minor splinter of thrust in here. And when I rotate that, I'm going to actually rotate that to the right. I'm looking, you start to build up a nice three-dimensional model for this roof. So again, the top, let's go back. The top is important, so the model will, the charge depth will be here, and then when it gets to here, it will drop down. So in here, will also be unblasted. So once we strip that bit of rock and that bit of rock, we're still left here with a bit of hard rock, which will be taken care of with ripping. So this is going to look at the situation with exploration holes separated in this section. It's about a 60 metre separation. This is getting up to 150, 200 metre separation. This is a bench of Leichhardt, so that's 120. And here we have a clue for Vermont, Leichhardt up here, and Leichhardt here. You can see that the mid-burden thickness is twice, or nearly twice, that thickness there. So you can see something's happened to over-thicken that mid-burden. There's a regular mid-burden here. Okay. The roof that you would expect in an exploration situation would be something like that. You'd be okay to model a roof like, a Vermont roof like that. So when we come along here with our drill rig, they'll be going down targeting that seam. And what they do, they go down and they go, well, I might have hit coal there while I pull up. Suddenly all the chips coming back up from the hole are black. That's not matching that roof, that model. So they'll adjust and then go further into their pattern and then go again, and then notice it's still going black, and then they might ring up the engineer and say that model's wrong. Further up here, they might be going expecting coal, and it's not coal, and so they go down again. So what you're left with is a potted roof for a charge. So it'll be going along and then down. The drill will be checking for the roof. It might go into the floor, into the roof itself, and then as they go merry along here, and thinking, well, there it is. They'll be leaving all this rock behind to be unblasted, so you get a potted, inconsistent drill floor targeting that roof. When I say drill floor, it's the depth, the bottom of the hole, which is the floor of the drilling. That's what. This is the drill holes that you're presented with, which is bear no relation to the Vermont model here. So what I do is I integrate the exploration and this suite of bore holes. What's happening here is you get 3 repeats in this thrust situation. So now the roof model is like this. So the driller in here can be working away, and we get a nice consistent drill floor targeting that coal roof. And then we can start to model the thrust main through here. And this, in fact, when I give this to the drill and blast engineers, this is approximately the region where you'll get a repeat. And there it is in the actual situation. So here again, this is the roof I was talking about, leaving behind that unblasted rock bed. But that's okay, because we can take care of that when we come back, when we strip this top piece off. So looking at in plan view, the drill hole spacing on the left here is a LOX line, and this is where, on this side, this is where the Vermont seam becomes split. So this is all Vermont seam as one, and here it's a LOX line. So you've got exploration spread. You see that there's a cluster of holes in here because they found an intrusion, so I just wanted to single that out. The blue lines represent the faults. This is a union of radii which is equivalent to what the contract says for us is adequate drilling to define the geology. But what we do, when we start to overprint the thickness variation that we're getting from that spread of exploration, we're getting these anomalies, and particularly along the thrust faults, we're getting repeat seams. And in here, this might be a normal situation, a normal fault situation where the seam has been attenuated. Up here, for example, I know it's a normal fault, and then strangely enough, there's a repeat there. So you can imagine trying to reconcile what's going on in here, these, what I call hotspots, they're not being confined by the expiration spacing. This is the intrusion I was talking about before. So just looking at, just changing subject, but the volcanic effects that we have in the coal. This is from Collinsville. This is the top of the seam of the Blake seam, and these cells represented by these oval eggs as they're talked about in the field. And what you'll notice is in here, when I zoom in, there's the roof of the last ply, which is economic, but the colour is changing in here. The colour has changed from, this is more vitrinite, less vitrinite here, so it's gone greyer. So what's happening is you're losing your volatiles and it's losing its economic value. I can see the difference between a higher vitrinite and a lower vitrinite signature in the density. In fact, we've lost that much coal. If that got into the product, there would be a specification problem and a possible rejection. You can see the ambient heat is leached into that roof in an interesting kind of way. Looking at the different pit at Vermont, it's called North Pit. This is our spread of expiration. And what we're going to do, we're going to look at an area in here. The blue is the spread of blast holes that I have to integrate. So I have a greater knowledge now of the green expiration and the blue blast holes. I'm going to look at this little patch in here because these green blast holes show that there was an intrusion there, but two isolated boreholes showing intrusion is not really enough to make a call to say, well, we need to move this top of our drop cut. Well, this is where we start. This is not dug, dug. So we start digging from here. We go down at an angle and we target a seam which is further out from the crest. But two boreholes here, would that be enough to make a call to say, no, I don't think that crest should be here. That's too aggressive. We want to actually move further. We want to avoid two boreholes. Should we do that based on two points? I don't think so. So that's why the crest was put here prior to the blast holes. When you put the blast holes in here, it paints a different picture. We're zooming into this area of intrusion. We're going to look at a transect in these blast holes, so 95 metres. And this hot spot has overprinted the Permian coal measures, and this is a dolerite, Cretaceous in age. It reminds me of what I studied at Victoria University, where you have a schist overprinted, a schist Ordovician schist overprinted by a Cretaceous granite. And if we now consider this as a schist environment, you have a biotite from out here and a biotite from in here. The biotite here is going to be high in iron, which is like an anite end member. And in here you have a phlogopite end member because the iron has been taken up by the pyrite. But in here, it's, in a coal environment, it's the vitrinite, which is giving up its volatiles at the expense of the heat. So looking at each hole, the density from F, E, D, C, B, A's up here. You can follow this navy blue density and see it gradually start to change. Here it's, you can almost say that that's obliterated, and here there's no evidence of coal. You can only really just make assumptions that the gamma, this red gamma is starting to kick to the right there's something muddy underneath the Vermont sand. So what's happening here, we have a vitrinite being replaced by inertinite. It's not as complicated as the biotite giving up its iron. It's just simply old wood being burnt, turned to charcoal. But you can see less dense and more dense in the coal. So you can start to draw it with a spread of overall boreholes. You can draw up an aureole and then advise the engineers that, in fact, we're experiencing a rather bigger intrusion than we first thought. It's a two-dimensional slice, so I can draw up that in 3 dimensions. So this is our mine plan. Had we just known that these 2 boreholes were intruded. So the mine plan, you start digging here and you'll target here. So it's taking that grey away. So here's our boreholes. Assume a dike situation rather than more of a lacquerless general intrusion environment. So with 2 boreholes, you can say, well, let's target the seam out here. We're going to get this coal in here and in here because this has been confined to 2 holes. We should be okay. But what it has shown is that blast holes have created an aureole which is far greater than just the 2 exploration holes. So we adjust the target. So we let go of this false coal because this is all being intruded. It's uneconomic. And to adjust the toe to here, further down it, you're saving the client vast expense from stripping all that waste rock away for no payback. So here are some numbers just to look at, going back to the thickness difference. This is a thickness plot. In plan view, 2 different strips, same strips here. This is with the blast holes, the thickness variation, and without blast holes, the thickness variation. These numbers represent the tonnes that would come out of here on a model developed from this drill hole spacing. Strip 1 would give you 100,000, strip 2 125,000. If we consider that something more closer to reality is a drill hole spacing more akin to 20 metres, this is what is actually there. Not exactly, but it's closer to what the reality. So we're going to reconcile back to exploration, and when we go and mine in here, I'm going to assume we're only as good as 96% of what is there anyway. Assume that these numbers represent what is there. So 96% of what is there is 96% of these 2 numbers. And so when we mine strip 1 and reconcile against a thickness model as determined by exploration, we've come up with 800 more tonnes, these are 800 plus, than what was predicted by exploration. So we can say to the mining superintendent, whatever we're doing in that strip is good. We're not losing any coal. So when you get to the next strip, keep doing what you're doing. But lo and behold, because there's a bit of a thickness increase, this hotspot I was talking about, we only get 96% of what is there, 96% of 119,000, we get 114,000, but this interpolation is creating a false sense of how much coal is there. There's not 125,000 tonnes there, there's more like 119,000 tonnes there because that's the number that's developed by So we extract 114,000 using the same method that we did in strip 1. This time we're finding, well, we've just lost 10,000 tonnes against a model which predicted 125,000. If we look at the 20 metre spacing, well, in fact, we lost 4,200 in that. If we consider now that our model is 105,000 and we took out 100,800, we're down 4,200, and then we can say to the superintendent, whatever we did in that strip, was bad. We need to adjust our stripping method, raise our charge, or change the tools, change the truck shovel, whatever. Something needs to change to be more supervision. So let's make a difference. Let's go from 96 to 98, and whatever change we made is 98% of what is actually there. This time we've taken out 116,000, whereas if we had made no change before, we would have lost 4,700. This just demonstrates reconciling against drill hole spacing, which is coarse, and reconciling against the drill hole spacing, which has detail. And so in summary, the objective of the geological model is to accurately reflect true volumes for reconciliation. That's what I was just talking about. The integrated blast hole and exploration model better reflects the true mining performance. So in the previous slide, had we known the correct number to target, we could have made an adjustment. And the blast holes, of course, create an accurate roof to be modelled and make my life a lot more interesting at work. Too long?
Well, thank you for this. To see how it's actually done within the industry, and examples that you gave really good. So I'll just turn to the audience and ask, are there any questions?
How long does it take to run one of these holes for a blast hole to get that information?
Your rate of drilling?
No, the geophysical logging.
Oh, well, we can do approximately 20 holes in one day. So, and we get them typically there for 2 or 3 days. And we do around 200 a month. And there's more being drilled in complicated areas where John Clee's wondering what was going on. Whereas if it's boring and predictable geology, it's more like 20 metre spacing, but we'll take it down to finer detail where it gets complicated.
You don't see much of a delay or turnaround from blasting design to being detonated?
No, there's a toll gate, if you like, that a sign-off has to be achieved before we can go and perform the blast. The accurate roof model has been made before we start drilling the overall pattern. So we can't sort of jump shortcut and go ahead and drill that pattern without knowing the correct placement of the charge data.
And it's not an active source that you're using?
Oh yes, it's an active source. Yeah, we have the natural gamma.
Yep.
It's talking about the picking up the mudstone, and then you have an active, which is the first run. The second run has the active americium beryllium source on the bottom that emanates its ions out and is received. That's right.
About losing a source?
Well, that's the reason why you run a probe with no source on at first, which is the natural gamma. It also measures the deviation of the hole. So I need to know exactly where, since it's a straight line, you can corkscrew right down.
These are our ticketing blasting guys.
So every hole has a deviation on it.
Yes, of course. Very interesting.
You didn't really talk about how you started on the measuring, the probe. So is this something on a rod that you lower down with your source on it, and you just reading off digitally what's happening? How are you gathering the information?
Well, the borehole has to go through the floor of coal. So the driller knows just to keep going. When he gets black chips coming up, just keep going down and make it approximately 6 metres below the floor. Once we have that sump of 6 metres, then we can drop the probe down, which would be a natural dummy run first, natural gamma, and the second run is synced with the source. So it comes back as a one digital file, and then it's not instantaneous. Like I have to be synced. I have to email the file, the ASCII file, and then create the squiggly line, if you like, and then make the interpretation off that line. So there is delay in getting the information back, say 4 hours.
So the modelling happens back at your head office, or the main, computer doing all the modelling back at the office, not in the fields.
That's right. Yeah, it's just the geophysicist will pick up the information and then has to drive back to a point where he can communicate that data back to me. Also, the surveyor has to pick up the top of the collar of the hole, exactly where it is in XYZ. So once I know where to start, then I know how far down the collar is, and I know where the hole is deviated to. So everything is as much precision as I can gather.
Now these ones we go through the floor of the coal. You've got the exploration drilling. Now you do some infilling. Do you do a planned infilling of a few of these to get the resolution before they do the main drilling? Is that how it works?
That's right. Where we can track the complicated thrust zones, we can request a tighter spacing. Where it's boring predictable geology, it's just more like every 20 metres, and that's just to go. So you got 60 metre strips bounded by high walls, and then along at the strike of the high wall, it's 20 metres, which is probably a bit of overkill, and where it's boring regular geology. It can be very complicated.
But what happens to those holes that you have drilled all the way through? Are they still used as a blast hole? Do they fill the bottom, stop the charge going into the hole?
They do for pre-split, because the pre-split hole is not a highly charged hole, but the vertical holes are backfilled right up to the top. So those holes are purely for the exploration of that accurate roof.
Do they fill it with drill chips or something to get it back up?
Yeah, we've got stemming that comes in. Yeah. Also, it's a trip hazard. You don't fill it up.
Any other questions?
It's very interesting work. So with these extra holes, have you looked at them obviously it's a cost benefit analysis being done to look at the extra drilling and the time of the geophysical logging versus the hole recovery that you're getting?
The cost benefit would be, we have a contract where we didn't do it, and we have a new contract where we are doing it. It's an open and shut case where we are doing it. We are achieving the contract target of coal. Nothing detailed has been done, but we have a suite of reconciliations before we did it, and a suite of reconciliations after. And it's an open and shut case, so it's beneficial.
There's one question there.
Simply to ask, how do your practices, do you think, compare with the general industry approach to this problem of defining coal reef?
I'm unaware of any other contractor or owner defining the roof. So to compare, I don't know about that. All I know is I'm unaware of it happening outside of text.
Others do attempt to define roof, to my understanding, but I'm not aware of anyone who is under the same incentive as you guys are. So, what you're doing is in direct response to a strong commercial incentive.
So you've got very good accuracy now on a coal roof. Have you tried or considered developing a blasting index? So to consider the whole interval instead of just the coal roof to improve or save costs, for example, on blasting?
You're talking about altering
For example, you showed
Power
that
factor.
had a mudstone roof considered mapping the entire overburn to, say, manage your blasting costs? Reduce energy?
Yeah, that's not my department, but I can advise on the charge placement, but it is possible to map that mudstone. And it has a lateral mappable extent. You can see it in exploration as well. That's another task. Maybe that's a subject for a paper.
Something. Are there any other questions? No? Well, I would like to invite you for coffee and biscuits, and actually if you have any other questions you can ask Helgi outside. So one more time I'd like to thank you.